So I'll be providing a short introduction about reinforcement learning and where its general uses and where we've used it in this project. So reinforcement learning, or RL, is a machine learning approach where an agent learns to make decisions in an environment to maximize rewards. RL is largely used to train agents to play games by interacting with the game environment, learning from rewards or penalties received for actions taken, and optimizing its strategies over time to achieve higher scores or game objectives. So the game we've taken to implement here is the popular pen and paper game Tic Tac Toe, and we've used two really popular reinforcement learning techniques, that are Q-learning and the state action reward state action approach, or SARSA. Now, the three major Python files that run this program are agent.py, teacher.py, and game.py. Now, in agent.py, the Q-learning and SARSA approaches are implemented, and they are inherited classes from parent learner class. The teacher.py implements the teacher agent, and the teacher knows the optimal policy for each state presented. However, this agent only takes the optimal choice with the probability set that is defined in the agent.py. Now in game.py, the main game class is found. The game class holds the state of each particular game instance, and it contains the majority of the game's functionality. And the main game is loaded using the play game function. I'll now be explaining the algorithms used in this program, that is Q-learning and SARSA. They are pretty similar except for the tail end, where the reward assigning is a bit different. I'll start with Q-learning. To update the Q values during Q-learning, the agent follows the following steps. It first observes the current state S, and then, according to the epsilon probability defined in agent.py, it selects between exploration or exploitation, because it knows the most optimal move, or it can take a random move of whichever one. Taking the known most optimal move would be the exploitation strategy, and taking a random move is the exploration strategy. So it comes in between epsilon or greedy. Now it performs the selected action and then observes the immediate reward R and the new state S dash. Then it calculates the maximum Q value for the next state, that is max Q of S dash A dash. So the new state and the new action is going to take the maximum Q value it can get from that. It then updates the Q value for the current state action pair using the Q value update equation that's defined in agent.py again. And then it updates the state S to S dash for the next iteration. So that was Q learning. And now for the SARSA approach, which is pretty similar, it observes the current state S and it selects an action using the exploration exploitation strategy. It performs the selected action and observes the immediate reward on the new state S dash, and selects the next action A dash based on the exploration exploitation strategy again. So it does it twice, and then it calculates the Q value for the next state action pair, QS dash A dash, and then it updates the Q value for the current state using the SARSA update equation, and then it updates the state to S dash and the action to A dash for the next iteration. So as you can see, they're pretty similar, except that SARSA looks two steps ahead and takes into account the next step as well. So now for the actual code structure, there are three main source code files in this program, that is agent.py, teacher.py, and game.py, as I mentioned before. The Q-learning and SARSA agents are implemented in agent.py. Each of the two learning agents inherit from its parent learner class, and the key difference between the two is their Q value update function. The teacher agent is implemented in teacher.py. The teacher knows the optimal policy for each state presented. However, this agent only takes the optimal choice with a set probability that is defined in agent.py. In game.py, the main game class is found. The game class holds the state of each iteration in the game instance, and it contains the majority of the game functionality. We'll now look at agent.py in detail. Agent.py has three class definitions. The learner class, which is the major parent class, and then the Q learner, which inherits from learner class, and SARSA learner, which inherits from learner class again. So coming to learner class, it contains an abstract function to be defined in inherited classes also. We'll see that later. It initializes common parameters, that are the learning rate alpha, the temporal discounting rate gamma, the epsilon value, that's the probability of random action versus choosing a random action versus choosing a greedy action, and the epsilon decay rate. Now, then it also selects actions based on current state, possible actions, and then its learning method of choice, and it also factors in the epsilon that was initialized in the previous function. It It also has an abstract function that saves the path taken as a pickle file. That will be concretely defined in the coming classes, in the subclasses. So it's different for Q-learner and SARSA learner. In Q-learner, that inherits from the learner class, it defines the abstract function using the Q-learning approach, and it does not need the A dash and S dash functions, S dash and A dash variables. And SARSA learner is the subclass inheriting from is another subclass inheriting from learner, and it defines the abstract function using the SARSA learning approach, where it does use the A dash and S dash variables.
Now we're gonna talk about the teacher.py file. So the teacher class implements a strategy for the teacher to play the tic tac toe optimally. This uses a combination of winning strategies, defensive moves, and fork opportunities to maximize its chance of winning and preventing the opponent from winning. Now there are different functions that are implemented in this py file. So first one is a win function. So this function checks if the teacher has a winning move available on the given board. Now it checks for possible wins in rows, columns, and diagonals. And if a winning move is found, then it returns the coordinates, which are the rows and columns of the empty cell, and which leads to a win. So the key parameter indicates the symbol used by the teacher. Now the next function that is implemented is a block win. So this function is similar to the win, but it checks if the opponent has a winning move available on the board. Like if the opponent has a potential win move, then the function returns the coordinates of the cell that has a that should be blocked to prevent the opponent from winning. Uh, the next function is the fork. So this function checks if the teacher has a chance to create a fork, like which means having two potential winning moves after the current move. So it checks for specific patterns on the board and where a fork opportunity exists. If such fork opportunity is found, then the function returns the coordinates of the cell to create the fork. Now next one is a block fork. So this function is like almost similar to the fork one, but if it checks if the opponent has a chance to create a fork, like if the opponent has a potential fork, then the function returns the coordinates of the cell that should be blocked to prevent the opponent from creating a fork. Also there is the center function. So this function checks if the center of the board is empty. Like if it is empty, then the function returns the coordinates of the center cell. Also, in addition to that, there is an init function. So this is a constructor method for the teacher class. It initializes the ability level of the teacher. Like uh, it determines the probability of the teacher making an optimal move. The default value of this parameter is set to 0.9. We have already seen some of the functions implemented in the teacher.py, such as win, block, send, etc. In addition to these functions, there are also four other functions like corner, side, empty, random move, and make move. So the first function, which is a corner, it this function checks if any corner cells of the board is empty. Like it prioritizes in picking the opposite corner if the opponent has occupied one. And if no opposite corner is available, then it returns the coordinates of an empty corner cell. The next function, which is a side empty, it checks if any side, like the non-corner cells of the board is empty. Like if such cells are empty, then it returns the coordinates of this empty side cell. The random move function is a function which chooses a random move from the available empty cells on the board. Like it returns the coordinates of any randomly selected empty cell on the board. The make move function, we can say it is a main method of the teacher.py. Like it determines the teacher's next move. So it follows a hierarchy of moves based on the optimal strategy. Like it calls other functions and it tries to win. It checks the center, it checks the corner, it checks the sides, and also creates a fork. And if possible, it also tries to block the opponent's fork. So and if such options are not available, then it makes a random move, like it returns the coordinates of a random selected cell. The this function, if such moves are available, like as we discussed the center side and all, such coordinates, such the coordinates of such cells will be returned, or else randomly selected one will be returned. In addition to all these functions, there is also an ability level parameter in the constructor. So this allows for some randomness in the teacher's move to make the game more interesting. So now we're gonna see about the plot agent reward.py, which is in the next slide. Now we're gonna talk about the plot agent reward.py. So the plot agent reward.py allows to run the script from command line, like providing the path to agent's data file as an argument. It loads the agent's data, specifically the rewards, and it plots the cumulative reward versus the iteration. So this file is basically used for plotting the cumulative reward versus the iteration. Now the first function, there are different functions in this, and the first one is the plot agent reward. So this function takes a list of reward as input, and basically it plots the agent's accumulated reward versus iteration. This function uses the matplotlib to create a line plot where x-axis represents the episodes and y-axis represents the cumulative reward. There is also a main function, like it only checks if the script is being run directly and not imported as a module. Uh, there is also one thing like the parsing command line arguments, and in this the main function of this is to create an argument parser object with a description, and it also adds a required command line argument which specifies the path to the agent's data file. The parses, then it passes the command line arguments and stores them in args variable. Then there is one loading agent data, and it checks if the specified path exists or does not exist. It also prints an error if the file does not exist, which is it is missing. Now the another function of this loading agent data is to open the file specified by the path, like in a binary mode for reading. Also, it loads the agent object from the file using the pickle module in Python. Now the last is to plot agent reward. The it it calls the plot agent reward function which we have like mentioned earlier, and it passes the rewards attribute of the loaded agent object as an argument. Now this function is basically used for plotting the reward versus reward like the cumulative reward using a np dot come sum. It is a function to calculate the cumulative reward over time, and then it plots versus the iteration, or we can say the number of episodes. Now Devakrishna will continue.
The game.py file. This file contains the game class, which uh, every game we play is an instance of this class. It contains all the functionalities to play the game. So the first, like when we when we create an instance of this class, we the constructor It needs one parameter, and there's one optional parameter also. The required parameter is the agent, and the optional parameter is the teacher. So the we can play this game in two modes, that is human user versus the agent, or we can automatically teach it using a teacher. So the teacher is optional, and the constructor also initializes the game board. The game board is a list of lists basically, and each element of each list is a string. So the first major function is the player move. So what this does is it queries the player for a move and updates the board according to that. So if there is the teacher, like if there is a teacher, then we query the teacher to make the move and update the board. Otherwise, what we do is we print the board, uh, then we basically tell the player to make the move, and we also check if the input they give is correct or not, is in the correct valid format. Then the next function is the agent move. So what this does is it updates the agent's moves. Uh, then check for win. So this basically takes a key value as an input. This function key value is basically the XOR 0, uh, and it returns if that particular key, uh, the particular player having that key has won the game or not. So it checks the diagonals. It first checks the diagonals for if it is in the winning format or not. Then it checks the rows and columns. If they are one, it returns true. Otherwise, it returns false. Then we are also next function is check for draw. This does is it basically checks every cell of the board, and if there is any cell free, it returns false, saying it's not draw yet. Otherwise, it returns true, which that is if every cell has been occupied by either x or 0, it returns true. Next is check for end. Yeah, this function checks if the game is still going on, or if it is a draw, or if any of the player or agent has won. What this takes as input is a key, that is x or 0. Then it checks if basically if the key x or 0 has won, and it prints it correctly, uh, it prints the if the player has won or the agent has won, like that. It then prints if it is a draw or not. The next function is the print board. This basically prints the board into the terminal, so the human user can see the board. Then there is the get state key. What this function does is it converts the 2D list. The board is, as I told before, is a list of lists. It's a 2D list, and this converts it into a string. So every a row is appended to the end, and then it's all converted into a string. Then the next is the uh, play game function. Yes, this is like the one of the main functions that it begins the game loop basically, and it takes an input called player first, which checks if the player is going to make the first move of the game. If it is then the player makes the move, and then yeah, after that we uh, get the state of the board, that is we call the get state key, uh, and we give the state to the agent, and with that we get the action of the agent. Then after this the loop begins. That is we make the agent do its move, then we check if we check for the if the game has ended. If the game has ended and if it is the agent has won, then we give it a reward of 1. Otherwise, if it is a draw, we give it a reward of 0. uh, and if the game is over, then we also break the loop. Otherwise, what we do is we make the player do the move, then we check again for the win, check if the game has ended, and if the game has ended, then we give the reward as -1 to the agent, because right now the player has made the move and the game has ended, so meaning the player has won. Otherwise, if it is a draw, then we give the agent 0 reward. Otherwise, what we do is if the game has not ended, the reward is set to 0, and we get the new state that after the appending the agent's move and the player's move, we get the new state of the board, and then we give that to the agent and get its action, and we also update the agent's Q values. Then the loop again begins, starts from the first. If the game is over, like when we are breaking from the loop, we again update the agent's Q values the one last final time for it to learn. The next function is start. This function basically is we are determining who's moving first, like that. Like if a teacher is the game has 2 modes, no? The teacher or the player, human player. So if the teacher is selected, if a teacher is selected, the game starts randomly. Like we use the random function to check, give a small probability like thing. So if, and otherwise we would give the user an option if they would like to go first, and based on that we start the game. That's it. Okay, play.py. Play.py is basically this file is it creates the user interface, the terminal interface for the user to interact with the game. So the class in this is called game learning. So this class holds the learning, the process of learning for the for the agent. So the constructor of this class, it loads if already there's a trained file of the agent, and if you want to continue the training, that this the constructor calls upon this file, and you can continue the training. Otherwise, if you want to overwrite it, that option is also there in this. Then you also define various parameters for the training, like as default itself we set alpha to 0.5, gamma to 0.9, and epsilon to 0.1. So if you want, you can change that also while loading uh, this class. Then uh, another one of the other major functions is begin playing. So this is basically like if the user wants to play, the human player wants to play through it, you give a number of you play with it, and it basically asks again, like, do you want to play again after the game's finished, and you can give yes or no and then continue playing again and again. uh, then another the next class is begin teaching. So this is to teach the agent by one of the algorithms, that is SARSA or Q-learning. So what this does is it we give a number of iterations of how much we want to teach. So it loops through the number of iterations. Uh, yeah, it loops through the number of iterations and teaches the game. Basically, each iteration is one of the game being played once, so it plays it again and again till our required threshold is met. Then the main function, uh, as we said, this is a terminal game. So we take command line uh, arguments and all as inputs. So this basically this is where the mode selection happens. So we take if we want to play it against the we if the human wants to play, or if we want to train it, everything is handled by the main function. Yes. That is play.py. This is basically a simulation run. Uh, we like run the game. So the image on the left, you can see that we are initializing a new agent and starting a game loop. The human plays with the agent, and by that we're training the agent. The images on the left, you can see that we are assigning a teacher, and then that is the first image on the right, and the second image is basically loading an existing agent and training it, like continue its training, giving it again training loops. uh, this slide is also same as the previous slide, but in the previous slide we were using Q-learning algorithm, and in this one we are using the SARSA algorithm to train the agent. This slide is basically the plotting the reward against the number of iterations we are running it. So the agent starts to learn about this is the Q-learning algorithm. For the Q-learning algorithm, we are plotting the reward and the number of iterations. So at about 22,000, after about 22,000 iterations, the agent starts to, there's a change in the gradient, and the agent starts to learn a little bit, and we start getting a positive reward at about 40 after about 40,000 iterations. This is the using the SARS algorithm. Here we need a lot more iterations. At only after about uh, some maybe about 70,000 iterations, there's a positive gradient. So this algorithm is like pretty slow to learn the game.
In conclusion, the applications of reinforcement learning algorithms, specifically the Q-learning and SARSA, on the game of Tic Tac Toe has proven to be a valuable and an effective approach. Through this project, we learned to explore the potential of these algorithms in improving the performance of the agent that is playing the game. Now, we found out the choice between Q-learning and SARSA depends on the specific requirements of the task at hand. Like the Q learning with its off policy learning approach was able to converge to an optimal policy even when the agent made exploratory moves. On the other hand, SARSA with its own policy learning ensured that the agent learned policies that directly took into the account of the exploration exploitation trade-off during the training. So, talking about the reinforcement learning, it has shown like great potential in solving complex problems and learning optimal strategies in various domains. So, the application of these techniques to games like Tic Tac Toe serves as a stepping stone for more challenging tasks and real world applications. Further research and experimentation can also be conducted to explore the advanced algorithms and to try out different game environments, and also maybe try out the multi-agent scenarios to broaden the scope of the reinforcement learning in game playing and beyond. The next slide gives the reference to the GitHub code. Thank you.